Okay, so let's go on to the next chapter. Actually, this is the first chapter. Okay, our first chapter is embedded systems. So what do you have here, right? So in this chapter, we will just look at what are embedded systems and uh, look at what they are. Okay, so this one is just like an overview lah. Okay, so no big deal. Just enjoy it, right? So first we'll take a look at what are embedded systems and what are the characteristics. So here we look at the overview of computing systems. Okay, to the layman, to the normal person, not in engineering, computers are either laptops, mainly today, desktops, getting rarer and rarer, and servers. Okay, very rare. Okay, not many people knows what are servers. So these are the computer, but when people think about computer, these are computers, but they're not that many compared to embedded systems. So embedded systems is really a computer, but much more. Okay, there's much more, many more of this in existence. And the term embedded means that it is attached deep inside something. So in our computer, we have a computer inside the mouse, a computer inside the USB drive, and everywhere lah. I think there's also a computer inside the USB hub, everywhere. So a computer inside a computer. Okay, so this is just to introduce the term embedded lah. Right, then the characteristic of embedded systems. The first thing, the first clear characteristic is that it performs a single function. Okay, normally it's not reprogrammable or not repurposable. Okay, the function in life is only one normally. It is the embedded system is part of a larger control system. So like in your mouse, the embedded system is the computer, but it's part of the mouse, and the mouse is being controlled by the computer. Cost and reliability are the most significant aspects. You want it cheap and you want it reliable. Of course, there are other aspects also, like power consumption and so on and so on, but these are the two most important things. Okay, billions of units are produced yearly versus millions for general purpose computers. In general, embedded systems do not provide end user programmability. Okay, so maybe like 99%, 99.9% of the embedded systems never need to be reprogrammed. And there's a rich variety of microprocessors, over 300 types. Okay, don't quote me on this. I read somewhere could be 400 by now. Who's counting? Okay, so when you're going to design embedded systems, these are the typical design constraints: small size, low weight, low power. And for military vehicle based equipment, they have this term called SWAP: size, weight, and power. But for us normal people, we don't care about this. But it just means that these three things are together. And then embedded systems are normally have to work in harsh environments where that means power fluctuations. Okay? So your power may not be 5 volts all the time. And then we have radio frequency interference, we have lightning, heat or vibration, shock, water corrosion, physical abuse. I think physical abuse and shock come together. And then embedded systems must have safe critical operations. They must function correctly and must not function incorrectly, especially where lives is at stake. For example, like anti-lock braking systems or airbags. Okay, your airbag must not function incorrectly, must not fire while the car is not moving. Okay, but if there's a kid playing there and he knock at the bumper, that's of course what to do. Who should they should not be doing that. Okay, and embedded systems have extreme cost sensitivity because they are mostly produced by the millions. So even small reduction in price in the cost of manufacture will convert to a big number. And there's also I added this, okay, from this set of notes. I added the point of repairability, ease of assembly and reassembly and replacement of internal components. So like there's a one website called the teardown website where they give a mark, where they give a score to embedded systems for computers, and mainly for computers lah, and computers and handphones. They give us ease of repair score. So it is an important buying decisions for consumer products such as mobile phones. Okay, so of course lah, now not so important, maybe not so important now because we just give it to the people who is going to repair, but the person who's going to repair will not like a mobile phone that requires you to open up 20 screws to open it. Yes, or to use a heat gun. Okay, so many mobile phones and tablets and even computers now, like my iMac, they don't use screw. Okay, they use glue. So if you have to repair something, you have to melt the glue first. If you don't do it properly, then you crack the LCD. So that will give you a very low repair rating lah. It's very difficult to repair devices like that. Okay, let's play around with Google a bit. Okay, so let's go to this website called the iFixit. See what you think. Okay. You can see here, this is a smartphone repairability score. iFixit, what they do is they tear down the smartphone and they look at what are the components inside there. Okay, a score of 0 means it's unrepairable. Okay, you bought it, it should last, and you should be able to fix it. So buy repairable smartphones. So these are some numbers. I think this one is sorted by release. Okay, so by date. So iPhone 13 is 6, Mi 11 is 4. Okay, look at the score here. Oh, I was thinking of buying this one. That's bad. Okay, the glass body makes drop damage more likely. Curved glass requires special tools, or like it's likely to break during repair. Okay, this is a danger lah using LCD now. To replace the built-in sensor, you need to replace the whole. You need to remove the whole display, which can result in a broken screen. But the good thing is requires only one Phillips screwdriver. Okay. Just now it says special tools. Suddenly it says Phillips screwdriver, only one screwdriver is needed. I don't know which one to believe. So let's see. This one terrible. Microsoft Surface Duo, score of 2. Batteries are glued. Requires extensive disassembly to service. And then uses uncommon 3-point screw. So if you see this screw, you need a special screwdriver that you have to go and buy first. Samsung Galaxy Note 3. Okay, iPhone 6, not so bad. And then here, Samsung 2. Why are Samsung's low scoring? And then we have Motorola Razr. Every repair starts and ends with stubborn glued-on outer covers. Replacing the battery requires near total disassembly. And so on lah. Okay. 10. Oh, this is everything can be replaceable. Okay, so there's one with 10. And what's the lowest? Is here. Essential phone. 1. Not sure here. You have to freeze the handphone to be able to repair, maybe. And so on lah. So basically this website tells us which phones to avoid. Okay, so the ones that are very difficult to repair will cost you more lah, and when you have to repair. This Fairphone, I've never heard of this phone anyway. Huawei 6, Xiaomi. Now it's 8. Just now there was one that was pretty bad. Anyway, just to show you lah. Okay, when you are buying something, that's something that you have to be aware of. Okay. All right. Another characteristic of embedded systems is power management. And for many applications, the low power desktop CPU are not really suitable. Okay, for example, Intel Atom, they call it embedded system. Even we have a course called embedded system teaching Atom. I see a chat. Okay.
Thank you, Doctor. It's me.
Okay.
Thank you, Doctor.
Okay, so for Intel Atom, it can go lowest can go is 1.4 watts and can go up to 13 watts, and Celeron can go to 10 watts. So 10 watts is not really suitable for battery use. So for many embedded systems, you need consumption of less than 1 watt, or maybe less. Okay, if you look at your USB port can only support 500 milliamps. 500 milliamps maximum lah. Okay, times 5 volts, so that's 2.5 watts. So, that's the maximum. So 1 watt is still okay for many embedded systems. And there's now there's a movement or a new term called TinyML, where you want to run machine learning on very low power devices. So the target is 1 milliwatts or less. Okay, so if your device can run 1 milliwatt, you can say it's TinyML cloud compliant, quote unquote. And many systems need to run for use on battery. For example, this sensor that people use for wireless sensor networks. So these systems, they normally use one AA battery 1 year. So if you have 2 AA batteries, they can last 2 years before you need to go to the site and replace the battery. So that means your design must be really low power. You have to choose your peripherals and CPU properly, and maybe do power management. Okay, turn off the system when not necessary. So definitely not suitable for Atom lah. Not going to be able to do that. One AA battery for 1 year. So that means embedded system itself has a range. Okay, so you can have the one that is low power, very low power, and there's also embedded systems that uses a lot of power. They're still categorized as embedded systems, but maybe totally cannot run on battery. A good example maybe like the processor inside a wheelchair. Okay, there's a smart wheelchair that can work on voice command and then can climb stairs even. There's a Pentium inside there. So you need a big battery for that one. Still embedded, so there's a big range lah. So anyway, need something that we need to be aware of. So when we need to have low power, we need to decide whether we need ultra low power or not, and then do we need fast wake up when needed. Okay, so this is a case where you tell the processor to sleep, and when something needs to be done, it wakes up. So and only then you use more power. And then there's also a movement today for green energy, so for energy harvesting. So you just use the heat around you or whatever energy is available around the device to power. So that means you don't have to have a special battery. So energy harvesting requires not a battery but a super capacitor normally. Okay, then and next characteristic of embedded systems is reliability. Must be reliable, or people can die. And one bad case of embedded system that failed was the Boeing 737 Max, which crashed twice. And there's one 737-800 that crashed 2 weeks ago in China. That one we do not know yet what is the problem, but kind of looks kind of the same. And then there's also our Boeing MH2664 to Tawau. Remember, I think last week it dove 7,000 feet. Okay, because of the fault, not of the system, not of, maybe not the computer, but the peripheral. And the pressure sensor was not working, and they didn't provide like a backup. So who to blame? Don't know. We don't know. We do not know, right? Maybe not the software programmer, but the system designer. They should add another sensor there. So if the first sensor fails, you should have another sensor. Okay, so traditional techniques for fault tolerance may work for embedded systems reliability, like replicated or duplicated hardware for everything. So for airplanes, they may have like triple computers there, but no point if there's three computers but only one sensor, and when the sensor fails, the aircraft crashes. So they have redundant processors, but not redundant input-output devices. That looks like it to me for the case of the mass flight last week. And then there's also the technique for distributed consensus, where you have computers that vote and then they take a joint decision. Okay, so when you do hardware, you have to be realistic on the reliability. So some components, they don't last that long, and you need to have special techniques to simulate the error or the reliability. Okay, and then we have also the time sensitivity of embedded systems. This one we will take a look on the third meeting. Okay, we will take a short look in real-time operating systems, but this is an overview. So all embedded systems are reactive, where you respond to external events. It's not proactive. It doesn't know what happens. It only do something when something happens. So when something happens, you want it to do something. So if you want the system to respond very quickly, then you call it a real-time system. And real-time in real-time system, the correctness is partially a function of time. So if you respond correctly but not within the time that is allocated, then it's a failure. So that's what we mean by correctness is partially a function of time. Okay, correct plus fast enough, then it's correct. So hard real time means you have absolute deadline, after which the response are useless, like anti-lock braking system and hard pacemaker. So if you respond too slowly, people already die, then useless. Okay, the system useless. And you can also have soft real time. Uh, the deadline is not so tight, but should not be too bad. Like a telephone switch. Okay, so you want to dial your phone, can be 1 second, can be 3 seconds, can be half a second. Doesn't matter that much. But you still need to be real time lah. So cannot be half an hour before you connect make the connection. So if you look at the step spectrum at the bottom here, you can see real time starts in the middle here, soft real time, cruise control. Okay, cruise controls. I have I have 2 cars with cruise control. So it takes few seconds to activate and to respond. So that's the situation. And then we have the telecommunications where I was mentioning the phone switch just now. And you have flight control. Flight control, yeah, depends on the plane. So on a fighter, it has to respond many times a second. Okay, every second the control surfaces must be adjusted very quickly. So, but still not so bad lah. For a few times every second, not 1,000 times per second. And then lastly, we have the electronic engine control. Okay, on the left side, we have totally non-real time. Okay, computer simulation can take days or weeks or months to simulate something. Okay, so some devices are not so easy to categorize whether it's embedded or not. Okay, so like a mobile phone, you have embedded systems traits like size and power constraints. Yes, limited system resources. Yes, the code is stored in flash. Yes, but then you have also personal computing traits like you can change the apps, and software failure is not life-threatening. Okay, so that means, yeah, just like a personal computer. And then the OS itself is not real time. Okay, on to the next section. How do we design embedded systems? So the design process of embedded systems roughly follows the design process of software. Okay, so in software engineering, which also I'm also teaching, in software engineering there are many software process models. So where the term software process model is applied to the sequence of things that you have to do to get the system running lah. Okay, so the basic one, the famous one is called the waterfall model, shown here. Okay, so where you have 5 steps: specification of the system, architecture level design, and then the low level design, implementation or coding. Okay, for software. So for hardware, you build the hardware, and then finally testing. So for waterfall, it's like waterfall. Once you move to the second step, you cannot go back. So that means you must complete the top step or top stage. Okay, any stage must be completed before you move on to the next step. And there are ways to go back, but very difficult. So the waterfall model is famous because it's easy to understand, but for systems that require re-engineering or redesign, it's not flexible. So that's why we also have things like spiral model, where we incrementally build a system, maybe build a prototype first, and then from the prototype you improve it, and you can maybe have many prototypes before you come up with the final version. So this is more in line with a normal way of designing things. So spiral and iterative, they are related, but the difference is how you draw the steps. Okay, here waterfall is drawn like this because we want to show it looks like waterfall. Spiral looks like a spiral. Lastly, we have the current one called the agile methodology, where all these 5 steps is done very quickly. So in a typical waterfall model, and let's say, okay, just for sake of argument, the system is going to be done in 5 months. Each step is 1 month. So first month you do the specification, then second month you do architecture, and so on until you finish everything in 5 months. So, but the agile methodology tells us that we finish all 5 steps in one cycle, where the cycle is 2 or 3 weeks, and the cycle time is fixed. So that means in 5 months, it's possible I go through these 5 steps. Let's do the math. Okay, 10 times lah. Okay, so it's possible that you also have the 10 versions of the same hardware. So agile methodology is most suitable for projects that require uh, some kind of proof of concept first, and also the user or the potential user or your manager can give feedback, but can be expensive because you are going to repeat many things before you come up with the final decision, a final version of the product. So people just use waterfall model for small projects, which doesn't require a prototype. Okay, so again, if you convert this waterfall model or agile methodology or something into flowchart, becomes like this, where the specification actually come up with a document. Okay, if it's a company that is going to be audited, you need to have a document which must be in a precise language and precise notation. So a good document uses unified modeling language. So this UML is covered in software engineering, not famous in hardware, but people use UML for hardware also. But the hardware must be software based lah. If it's totally hardware, you don't use UML. And then we go to the architecture design, where you partition the system into major blocks, major components. So hardware could be processor selection and peripheral selections, and the software, what are the major software functions. Okay, then we split to the actual hardware and software design, where the hardware and software engineers work independently. So at this moment, you take the big blocks and make smaller blocks, and then do the actual work on the smaller blocks. And finally, not finally lah, second last, we have the integration, where we put them together. And integration is going to discover a lot of bugs because things don't fit together as well as predicted. Even though we have completed the design, integration means going back and fixing things that are supposed to work but doesn't work. And then the testing is to test the product as a single device. So for embedded system, you have to test really really carefully, because some products have a life and death attached to it. So if you are doing system with co-design, okay, if you're doing things, if you have a project which is based on FPGA, and you can use high-level synthesis, which is also offered in another course, okay, in our program. What you will see is that you will do the architecture, and the software design is minimized, or the split is delayed. Okay, you try to assume that the hardware and software are equivalent, and you want to delay deciding whether this component can be done in hardware or software late. So you model everything in software. Of course, modeling is in software, but deciding whether the component should go to chip in hardware form or as a software form is done very late. So in that case, the debugging is easier, but the methodology is quite new lah. So it's called hardware software co-design. Okay, so it's the hardware software co-design is an example is used when some applications can be done either hardware or software. Okay, so take the digital camera example. The images are compressed in JPEG, and you can implement JPEG either hardware or software. So which one do you want to use? If you choose wrongly, you will waste more power. The product will cost more and so on. So same algorithm, but can be implemented many ways. Whether totally hardware, okay, like ASIC, or you can do programmable data path like FPGA, or you can use application specific processor or DSP or GPU, or you can use extensible processor like RISC-V and ARC processor. Not so famous, but they are there. And then completely general purpose microprocessor, okay, like the ARM or the Intel. So these processors, once they arrive on your desk, you cannot modify at all. But for extensible processors, there is a possibility for you to add a few functions. Okay, some functions may be better in hardware, so you identify which parts have to be accelerated, and you only modify that part. So these are comparisons of the five methods of implementation just now. Okay, so general purpose processors are always on the left. The engineering cost lowest, performance per watt lowest. So basically, for the amount of battery power that you use, it gives you the lowest performance. Unit cost is highest, and the flexibility is also highest. Okay, it's very flexible because to change the function of an ARM-based product, you just need to reprogram. But for the rest, it gets harder and harder to change the function. Okay, so of course the hardest will be ASIC, where everything is fixed from the moment it come out from the factory. So the reason people use ASIC is because unit cost is lowest, right? So you have this. We always have this range of implementation technologies. Okay, so which path to take is mainly determined by volume and or performance. Okay, so if you need to create your product a lot and maybe millions of the same chip, then you go for ASIC. Okay, of course, but and also performance lah. So maybe you only need one copy, but you want absolute performance, and the price is no problem. Okay, like the Javelin missile that they use in Ukraine now. Okay, so I don't think it's FPGA or DSP or something. Sure, it has to be ASIC, because once it's ASIC, you cannot change it. So no matter what happens, the programming or the function of the missile still the same, and they cannot upgrade the missile, right? It's not like a camera or a phone, for example lah. You always have OS upgrades, but even cameras can have firmware upgrades. But missiles, don't think so. There's no like version 1, version 1.0 upgraded to search more targets. They don't change it. But on the plane, yes. Okay, like the F-35 fighter is the most expensive weapon system in the history of the US. The whole airplane can be upgradable. Okay, the radar can be upgraded. Even the tools to detect the even the diagnostic tools can be upgraded. Okay, so like if the technician want to know what is wrong with the plane, they use a special machine. So even the machine can be upgraded. So that's why it's costing a lot, and a lot of bugs even today. Okay, so the F-35 is not bug free. Okay, when you want to design with the system, you have to consider all this. The the things that I mentioned. But if something needs to be measured, we call it a design metric. So all these all these things have to be measured, and people decide which one they want to optimize or prioritize. Okay, next we go to the cost to produce an item, an embedded system. Okay, total cost is the NRE, which is the non-recurring engineering. Somehow I did not put, oh here, okay, non-recurring engineering, okay, NRE. Okay, this thing happens only once, okay, for the life of the system. Okay, that's the total design cost. And then for each item, you have to calculate the unit cost times the number of units. Okay, many embedded systems, they become cheaper as time goes on, because one is because they get better in manufacturing. The other one is because you spread the cost of NRE, just like the F-35 fighter I mentioned just now. As more people buy the plane, maybe 800 million now become 600 million per copy, because you divide the trillion dollar by 100 before for the US maybe, and by the time Singapore managed to buy it, there's already like 800 units in service. So now the NRE is like $1 trillion divided by 800. So they get it cheaper. So the longer you wait, the cheaper the plane comes. Not more expensive, but become cheaper. So the per product cost is the total cost here, which is this number divided by the number of units. So the more units you produce, the cheaper it will be lah. So here is the final value, the NRE cost divided by the number of units. So if the number of units is large, so this figure here, becomes cheap. Okay, but you cannot change this one. But sometimes even this can become lower, because people get smarter in manufacturing. They can see things that they can see things that they can save money. So of course, this one will become lower because you divide by more units, but even the unit cost here can become lower. So that means the volume of the number of units that you make is very will decide what kind of engineering that you want to use on it. Okay, so here is some examples. Wait, only one example. So NRE is 2000, unit cost is 100. So for 10 units, the total cost is 2000 plus 1000. Total is 3000. Per product cost is 300. So amortizing or spreading the NRE cost over 10 units results in an additional $200 per unit. So more units manufactured, the lower additional cost per unit. So let's say we are using the same component now. We make 20 copies. Okay, let's make this 20. So what is the per unit cost? Per product cost lah. Okay, so then you'll have 2,000 divided by 20 here. Plus 100. Okay, so now it's cheaper. 100 plus 100 is only 200. Okay, per copy is now 200 if you make 20 copies of the same thing. Okay, this is a graph which is this is an approximate graph to cover to show that time to market or the speed of getting the product for sale is very important. Okay, so let's say you are product green. Okay, the green line is product A, which is by the market leader. Okay, and you are company that just follow trends. Okay, just follow the trends. So you see this product being released, announced to release, you design. Okay, and then you spend more. Okay, you spend more compared to that guy. Okay, so because you are delayed, okay, your NRE cost will be low, more. Okay, your revenue will be more negative than the first guy. Okay, and then you have to sell the product. Okay, and then because of a delay, you sell less items. You sell less items, and then over a amount of time, this is the total number of profit you get lah, right? The total of the profit is this one, this area minus this area. Okay, this is the area where you sell the product, and then there's a peak. Okay, there's a peak there because a product can achieve popularity and then people don't buy anymore. So as long as this area is bigger than this area, okay, this area bigger than it, okay lah. But if you are good, okay, you design very quickly. So you design very quickly and then you immediately go to market early. Okay, here. Okay, you design early, put to market early, and then your area will be big, right? So this is your money that you make. So this is your revenue minus your cost. So this one is quite big lah. The difference is maybe many times. So like your profit maybe 10 times your cost, but the other company, because of the delay, maybe twice only. Okay, so you put in 1 million, you only sell 2 million, not so much, something like that. So product with long design times equal more NRE costs. Okay, so if you if you design too long, okay, then you will spend more money. The total cost is more, and then the sale is less, because no matter what you do, people will not buy the product anymore. Okay, because everything nowadays follows a trend. So you try to design everything quickly. So that is why not just the cost, okay, like this one, okay, not just the cost is important, but also the time. So time doesn't appear here. Okay, time to design, maybe, okay, maybe this is fast. Maybe this is fast. We do not know. Okay, so this one is something that is depending on the company. So definitely this one is very slow. So time to market, sure, slow for ASIC lah, but FPGA not so bad. Okay, and then we have also performance metric. Okay, right now here we have the design metric and we have the processor metric. When we want to compare processes, how can we compare? The basic one is of course the processor speed, but what is speed? What is speed? It's not only processor speed but also many other things. So that's why we on the next chapter we have just a few slides on benchmarking, and then we have latency or response time, time between task start and task end. Okay, when you press a button, how long does it take for the camera to actually take a picture? So in the early days of digital camera, this is really bad, but now it's almost instantaneous. Okay, that's why digital camera had a very slow start. People at that time still use film. when digital camera came out the first time. And then we have also the term throughput, which is task per second. So can the product do more than one thing at a time? And then we also use the term speed up to compare the throughput for two systems. Okay, lastly, let me check how long is it? I think we just finished with IoT and then we take the break we take a lunch break or midday break. Okay, is it okay, everyone? Okay, just finish this one and then that's it for this morning. Okay, IoT. Okay, so this one is a new section which I added last year. Okay, so a review, right? So the IR 4.0, that people keep on saying nowadays, consists of also you have to refer back to IR 1, 2, and 3. So first industrial revolution was mechanization of, if I'm not mistaken, mechanization of agriculture, where we use machines to do the work of people. Okay, also maybe like making clothes from cotton, So that was 1765. That's the date that we see. And then the second revolution is mass production. I think famously this is also the Ford T by Ford, where they use assembly line, and this was made possible by electricity and oil-based power. And then the third revolution is automated production, supported by IT. And then here, fourth revolution is new technologies based on IoT, AI, big data, cloud, cyber physical system, and so on. Okay, so if you are going to do your assignment for this class, you should look at these terms, okay? Not just this part, okay? If it's only something that you can do electronic, just some IT, you don't comply IR 4.0. So one of your assignments is to propose something that apply IoT or AI. That is what you're going to do with your processor this semester. I think you heard it from your seniors, right? So don't worry too much. Most of you survive anyway, right? So here is the explosion of Internet of Things, explosion of IoT. 1992, people start with 1 million devices connected to internet. Now we are somewhere here, 2020, 50 billion and more, okay, and going up. So everything is connected to internet nowadays. So this is the IoT part, okay? So even very simple things, like I see a toothbrush here, I don't know, and this looks like a toothbrush. What's the point of connecting a toothbrush to internet? I don't know. uh, yeah, automated door lock, I've seen this, not so expensive actually. Okay, Samsung one maybe cost 2 or 3,000, but China made 500 or less. Okay, you can control your door lock from the internet. That one we can already buy from Shopee or Lazada. Okay, so the IoT again. What is in an IoT environment? So you will have an embedded system of two. We will have two embedded systems. One is the IoT device itself, which could be very simple, not running an operating system. Okay, so we are going to build this one, and we need to connect to an IoT gateway. So this one looks like the Wi-Fi router. Okay, the Wi-Fi router is also an embedded system, a bit more smart. It is also an IoT. Okay, it is also an embedded system, but normally there's an RTOS there. There's a real-time operating system inside your Wi-Fi. So you need to go through this gateway. if you want to hack your Wi-Fi gateway, you can, because many of the Wi-Fi gateways are hackable. You can modify that, and then and you can also buy a Wi-Fi gateway that was hackable from the moment you purchase. It's a hackable Wi-Fi. It's advertised as a hackable Wi-Fi router, and such thing exists. So you can add things here, and then from there you go to the network. So here you go to your Streamic, Unify, or Maxis, or whatever lah. And then from there you go to the cloud, where the cloud is just a term for servers. Okay, servers, they are somewhere there. You do not know where they are. Could be in Skudai, could be in Penang, could be in Cyberjaya, and then the cloud lah, or could be in US, could be in Israel, like Wiz, right? I think Wiz is Israel based, so don't know whether our data really goes there or they just stop in Singapore. We don't know, okay, because it's in the cloud. And then we have the applications. Okay, so from all this data, we can generate applications. So for example, your the Wiz, right? For Wiz, basically you have both at the same device. Okay, your embedded system, your handphone, send your location or your speed of your car, and then you also use the handphone to run the application. But there are other things that you can use from your phone that doesn't require your handphone. So that's why we have different devices. So if you look at this pipeline, there's no PC anymore. Okay, so applications normally now run on mobile phones, and your PC is to create the cloud app, or the app on the mobile phone. Okay, and then we have this term, cloud computing and edge computing. Okay, so when you have IoT, the computing is done in the cloud. Okay, for example, the Wiz that I mentioned just now. Okay, we ignore the fact that it's not really embedded system, but the the calculation of the shortest path is done in the cloud. So that is cloud computing. But there are many applications that don't require the data to be sent all the way to the server. Okay, so this is the age of the edge computing. Okay, the time for moving the computation from the cloud to the edge. Okay, many applications, there's no choice. You have to go to the cloud data center to do the calculations. But there are many things now that doesn't have to be computed at the data center. For example, the traffic light lah. Okay, assume that we have a smart traffic light, which require a cloud to do the calculation, to do the timing, or to switch the lamps. Okay, so maybe something like that lah. Okay, we're just making one very simple example where it's actually very simple, just to put the controller on the junction itself, and we don't have to send data to the cloud to do the calculation. So the computing is done at the machine itself, at the traffic light controller, and the traffic light controller become autonomous. Okay, maybe it receive command from the control center to blink yellow when Prime Minister comes, and so that the ambulance cannot get through, or something like that lah. Okay, something like that. Or maybe like in the if you look at the Italian job, okay, you can reprogram the traffic light. But most of the time, the traffic light will be autonomous. So there is edge computing, where the computing is done at the edge. But where is the edge? Okay, so many references say the edge is here. Okay, it's the edge of the network. The IoT here, not yet. The cloud, the network doesn't. If the computing is done in the cloud, it's called the cloud computing. If the computing is done in the IoT gateway, it's called the edge computing. If the computing is done in the network, okay, some of the calculation is done in the network itself. It's called fog computing because it's blur, right? Not edge, not cloud. It's fog computing. But for the really edge device here, at the last part here, we can also call it edge computing. So edge computing is not very clear, depending on who you're talking to. At least from my aspect lah. Maybe some of you have different ideas, or you read somewhere else. You can tell me lah where if I got it wrong. Okay, so anyway, the point is, what is the advantage of edge computing? What is the advantage of not sending data to the data center to do the computation? One is real time. Okay, data is processed closer to the source, reducing latency, improving responsiveness. Okay, so this is the example. For example, for the example of the traffic light, doesn't matter that much because you can have 5-second delay, people don't notice. But let's say you want to do voice recognition to open your door lock. Okay, open lock, for example, open door, and you are desperate because a dog is chasing you. So here 1 second is 1 second or 2 seconds makes a difference. So if the door can recognize your voice, it can open the door. If the door lock can recognize your voice, it can open the door quicker than having to send your voice to the cloud. Okay, this is a crazy example lah, just the one I can think of. Okay, because I mentioned the door lock just now. And then another advantage, energy and cost saving. Okay, so if you transfer information across the network, you require energy and resources. Whereas if the device itself can recognize your voice, the power required maybe the same, okay, or maybe just slightly more than when the product is not doing the processing. And then there's less network traffic because you can see there there's so many devices being connected to internet. So you don't want to go to the internet unnecessarily because network bandwidth is already limited. So you can overwhelm the cloud. So if there's a traffic jam in the cloud, your voice cannot get transmitted and the system cannot do recognition for you. And finally, data privacy. Because the computing is done at the edge, you don't have to transmit data anywhere. Data is localized. So now, here comes the killer app. Okay? So of course, at the edge here, you can run many things. But there are many apps. Okay, if you look at the Gartner hype cycle, you can look here what are the many types of app that you can run. But the Edge AI is the killer app right now. Is somewhere here. Okay, it's reaching its peak. So in 2 or 3 years, it's reached maturity. So here, what we have here is you have AI at the edge device itself. If you look here, these are all quite new information. Okay, and this is what we're going to do. Okay, so we're trying to target AI at very low power, and the scheme of things is called TinyML, where TinyML is broadly defined as a machine learning tools and techniques for on-device analytics at 1 milliwatt or less. And 1 milliwatt is actually 1 button battery for 1 year. Okay, this is even smaller than I mentioned 1 AA battery. So TinyML devices are getting very popular now and has a very big economic potential. Okay, so not all applications can use TinyML. So you have to know what you want to do. So the current focus area is keyword spotting, where the device listen to audio input from a microphone and respond only to specific sequences of sound. Okay, this one quite easy to do. Even my FYP degree people, students can do. So should be something you should think of. And then we have visual wake words. Okay, so wake words are something that was borrowed from the keyword spotting. Okay, so when the device is sleeping, you wake it up with a wake word. Okay, for example, Siri. So the moment you say "Hey Siri," it wakes up. Otherwise, it's sleeping. Like any iPhone, the iPhone is sleeping. The moment I say "Hey Siri," it wakes up. So it's a special word to make it wake up. So now, if the edge device, if the IoT is connected to has a camera, so you can make a visual wake word instead of audio wake word. So let's say you have a camera on your door. So seeing somebody will wake it up. Okay, otherwise it will just sleep most of the time. So it will save power, but it will enable it will enable more further processing after it recognize a person is in there. Okay, so first sleep, but sleeping while monitoring a person, if a person is there or not. If there is a person, then take the image and process further to know whether it's you or not. So visual wake words is something that is related to audio wake words, where the audio wake words normally is like to wake up the handphone, and then only you listen to the command after that. And then the last one is anomaly detection. Okay, predicts and informs when a device is just about to break. Okay, the reason we want to do that is because we want to maximize the operational life of the system lah. So if you know it's about to break, then you can call up the technician and fix it. But as long as it works, you want to use it. You want to use until it's just about to break. So you don't want to repair too soon because you will waste money. So this is one area where artificial intelligence can help to save money for if when you have a lot of the same devices in in factory, for example. Okay, so I think that's it for this morning. So we continue at 2 o'clock.